Welcome! We are talking today about Green's theorem. Now, who was Green? Well, George Green was a man living in the early 1800s, and he worked in his dad's windmill, but found that very boring, so, like you do, he taught himself calculus. He didn't have any formal education, but he decided, I want to know how calculus works. And then he said, I'm interested in electricity. How does electricity work, mathematically speaking? And so he came up with a whole model. In 1828, he published a paper describing how electricity works. He was the first one ever to do that mathematically. And unfortunately, it wasn't very well known in his time. He sold exactly 51 copies of that paper. But after he died, Lord Kelvin found one and spread it around, and it eventually became very popular. Now, one of the first observations that Green made about electrostatics, is if we had some sort of shell and we had a charge on the surface of the shell, if you're at a point inside, you're not going to feel anything. All the charges balance out. So, now the whole balancing idea is key, and eventually leads to the idea that if I have a charge in here, it's going to be on the surface. If this were a solid metal plate instead of a hollow one, and I charged it, all the charge would go to the surface. I'm told that's why if you're in a car and are struck by lightning, you won't feel anything, because the lightning goes entirely on the surface of the car and doesn't go inside. If you had a flat metal plate and charged it, the charge would all be on the boundary. So what does that have to do with calculus? Well, what it says is that if we want to sum up what's going on the inside of a surface, it is in some way connected to what's going on the boundary. And that's really the essence of what's called Green's theorem. And so that's what we're going to talk about today. How you can relate, if you have some closed surface, the double integral across the inside to the line integral across the outside. So that's the core idea we want to have here. So let's define our terms first. Okay, we are recording. I always get a little paranoid about that. So the positive orientation of a simple closed curve is a counterclockwise direction. And by the right-hand rule, it points out of the page. So as you travel the curve, the interior is on your left. Now, if you're not sure what the terms mean, a simple curve means it never crosses itself, and closed means that it ends at the same place it started. So, closed, I think that's clear enough that something on the inside can't pass to the outside without going across it. Although I'm told it took several hundred attempts to prove that. Anyway, so when you imagine walking along the curve, you should always imagine the interior is on your left. And so then we can define the curl of a vector field as del q del x minus del p del y. And that represents rotation around any point. So we can do that as a matrix. I get the order mixed up sometimes. So we put the derivatives on top, and then we put p and q below. And so we get del q del x minus del p del y, and that's called the curl. They don't usually call it the curl, but it is. It's just a two-dimensional version of it. And it represents rotation around a point. So let's do an example or two of calculating the curl. So let's take this field, x squared I minus 2xyj. Let's find and interpret the curl at 3, 4, 3, 0, and 3, negative 4. All right. So let's draw a picture here. So the curl, well, del q del x would be del over del x of negative 2xy, which is negative 2y. And del p del y is del over del y of x squared, which is 0. Or if you want to write it in the matrix form here, p is x squared and q is negative 2xy. So you get negative 2y minus 0. So the curl of f is negative 2y. So if we'll pick a few points, 3, 4, the curl of f at 3, 4 would be negative 2 times 4, or negative 8. This is negative, so remember, a positive direction means counterclockwise. So what this is saying, you want to picture this is like turbulent water. There's this function, this vector field, x squared I minus 2xyj, is describing how the water is moving. If you were to put a paddle wheel right here at 3, 4, the water would be spinning it in a clockwise direction because negative curl means clockwise. If we did curl of f at 3, 0, well, that would be negative 2 times 0, which would be 0. So here at 3, 0, there is no curl. It means that if you were to sit there, the paddle wheel wouldn't rotate. Maybe some of it's moving this way and some of it's moving this way. Maybe. And they would cancel each other out because one of them would try to move it clockwise and one would try to move counterclockwise. This is about the net effect. And it's saying the net effect here would be 0, so it would not rotate. And then if we went to 3, negative 4, the curl of f at 3, negative 4 is negative 2 times negative 4, which is 8. So that's positive direction, so it will go counterclockwise. Okay, so that's how we calculate it. So that is saying the curl at that point, or at a very small neighborhood around that point, and you would use a limit to get that exactly. So, now that we have an idea of what curl is, let's describe what Green's theorem is. Let's go ahead and state it. So Green's theorem says, we let C be some positively oriented, piecewise smooth, simple closed curve. That's a lot of words. Positively oriented, so counterclockwise. Piecewise smooth, so there aren't too many sharp corners. There are maybe a few, but it's smooth everywhere else. Simple, meaning it doesn't cross itself, so no figure eights. And closed, meaning that if you pick a starting point and go around, you'll eventually come back to that starting point. And let D be the region bounded by C, so D is the interior. If P and Q have continuous partial derivatives on open region containing D, so that means the smoothness, the derivatives have to be just a little bit bigger. Let me explain that real quick then. If we had, say, our curve was like this, we'd maybe draw a tiny little bubble around there. And as long as the derivatives exist and are continuous in that bubble, as long as the bubble's just a little bit bigger than our region, then we can go ahead and use Green's theorem. So we don't want to have any breaks in the derivatives in the function, in the region, or on its boundary. But if we have that, then the closed integral around C of P dx plus Q dy is the same as the double integral of the curl across the interior, which would be del Q del x minus del P del y dA. So you want this separated into P dx, Q dy, and then you sort of switch the order and you put a negative in front of the P and you take these cross derivatives. Or you can use the matrix, the determinant representation like we said before. Now notice that if it's a conservative vector field, that this was the expression we used to tell if a vector field is conservative, if these two pieces were equal, which would mean the curl would be 0. Conservative vector field has curl 0 everywhere, and so that would mean that the integral would also be 0, which would mean the line integral would be 0. But we had a theorem that closed line integrals or curve integrals of conservative vector fields are always 0 anyway, so it all matches. It all fits together. So what kind of we're saying in a weird way is that if we add up all the little curls inside a region, we get a big curl around the outside. So let's do an example here. Let's evaluate x to the fourth dx plus xy dy, where C is a triangle with vertices at 0, 0, 1, 0, 0, 1, travel counterclockwise. So let's do that. All right, here's 0, 1. Here's 1, 0. And so we have, let's see, what was our question? It was integrate along C, or this will be C. And we're going in the counterclockwise direction. So again, imagine if you're a bug walking along this boundary, the inside is always on your left. X fourth dx plus xy dy. Well, if we were to try to do this directly, we'd have to have a parameterization here for C1, C2, C3. We'd have, I guess, t comma 0. Then this would be y equals 1 minus x. We'd have t comma 1 minus t. And then we have 0 comma t. And we have to do 3 separate line integrals with 3 separate parameterizations. Or we can use Green's theorem. What would the curl of this be? Well, del x, del y, x to the fourth xy is y minus 0. So this would be the same as just doing the double integral across, let's call this d, of y dA. I don't know about you, but to me this looks like easier. It's a double integral, but it's a not very complicated double integral. So we'll say, okay, let's set up some bounds on this then. Y, I'll do y first. I could do x first. It would be about the same. Well, y would go from 0 to 1 minus x. Then x, here's at 0, 0, will go from 0 to 1. If you want to do x first, x would go from 0 to 1 minus y. Okay, and then it's pretty mechanical from here on. 0 to 1, y equals 0 to y equals 1 minus x of y squared over 2 dx is 0 to 1 of 1 minus x squared 1/2 dx, which would then become 1/2 times integral from 0, or evaluate from 0 to 1 of 1/3, or negative 1/3, 1 minus x to the third. And then if I plug in, I'll get negative 1 over 6. Bracket, if I plug in 0, I get 0. If I plug in 1, no, sorry, if I plug in 1, I get 0. If I plug in 0, I get 1. So 0 minus 1, which would be 1 over 6. That's my answer. And so, yeah, I think that's a lot easier than having to do 3 separate line integrals. So a problem like this, I most likely wouldn't tell you what method to use. I would most likely give you a line integral, and maybe it's easiest to do it directly as a line integral, or maybe it's best to use Green's theorem to simplify it. And that would really be up to you to figure out which way is best. So let's look at this next one. Okay, now look how ugly this integrand is. So this is a hint. If a problem is like this, evaluate 3y minus e to the sine x dx plus 7x square root of y fourth plus 1 dy. I don't know how I would do an antiderivative for e to the sine x or square root of y fourth plus 1. It might be possible, but it would be very hard. So when you see a line integral like that, so ugly, that's almost certainly saying you're going to use Green's theorem to deal with it. So let's do that. So the curl here, del x, del y, and this is 3y minus e to the sine x. And this other part is 7x plus square root of y fourth plus 1. Let's go diagonally. 7 minus 3 is 4. So the circle integral of all that, I'm not going to rewrite it all, is equal to the double integral d of 4 dA. Okay, so that just means it's 4 times the area of D. What was D? It was circle with radius 3. So, well, we know how to find the area of a circle. It's 4 times pi times r squared, which will come out to 36 pi. You could also do it as a double integral. You could convert that to polar coordinates. Double integral of 4r dr d theta r from 0, 3, theta from 0, 2 pi. And it would work out to the same thing, but, you know, why bother when you already know the area of a circle? And so, again, what this is kind of saying is if we have this circle, at every point we get little curls. And it's kind of amazing here. If you add up all those little curls, it's kind of like the same as if you do just one big curl around the outside. I know it's not technically curl around the outside, but it looks similar. It's all these little counterclockwise vortices on the inside add up to the same as the one big rotation around the outside. And in a way, it's kind of the same thing as the fundamental theorem of calculus, because the fundamental theorem of calculus said if we want to integrate from A to B along some region, it's the same as the antiderivative of B at B and at A subtracted, which is another kind of surprising thing. It's saying if we add up all the things that's happening in the inside, it's the same as just doing the end minus the start if you do this antiderivative here. And so this is kind of a recurring theme in calculus, is that you can take what's happening at the boundary versus what happens in the interior, add it up, and they come out to the same thing. Give or take doing a derivative or an antiderivative midway through. Okay, let's do another example. What if we want to go the other way? What if we start with an area integral and want to change it to a line integral? Well, the area is the double integral of the 1 function. So if we can find a function whose curl is 1, then we could change it into a line integral. And there's probably more than one, but this is the most common one. The area then would be 1/2 closed integral of x dy minus y dx. You can do the curl on that, and you can see it'll come out to 1. You do that. Yeah. So, let's do an example then. Let's find the area of an ellipse. X squared plus y squared x squared over a squared plus y squared over b squared equals 1 by converting to a line integral. Maybe you already know this formula, but here's a way of finding it. So we have an ellipse. This is A0, and this is 0B. And 0, negative B, and negative A, 0. And so if we want to know what is the area of that ellipse, the interior is D. So we'll say that means we want to know what is the double integral over D of dA. 1 dA is implied. And our formula says that it is the same as 1/2 the path integral of x dy minus y dx. So we need to get a parameterization. The parameterization, which I insist you memorize, is that x is a cosine t, y is b sine t. Then dx is negative a sine t, and dy is b cosine t. So, we'll put this together. 1/2. The bounds would be 0 to 2 pi. And if you use theta instead of t, that's the same thing. So, okay, x is a cosine t, and dy is negative a sine t. Hang on, do I have that right? Yeah, I think so. Oh, dy. That's why it was x dy. Sorry, I wrote dx. X dy b cosine t minus y is b sine t, dx is negative a sine t dt. So expand that out. It's 1/2 0 to 2 pi of ab cosine squared t plus ab sine squared t dt, which is going to be 1/2 0 to 2 pi of sine squared plus cosine squared is 1, so ab dt, which then just becomes 1/2 times 2 pi ab, or pi ab. And that's your answer. Notice that if this ellipse were a circle, that means a and b would both be the radius, r, and so that would just become pi r squared. All right. Let's go on. Let's go on to the next. Now, one of the rules can happen if we are not simply connected. Our region is not simply connected. So let me explain what this means. F of xy equals negative yi plus xj over x squared plus y squared. I want to show that the integral f dot dr equals 2 pi for any positively oriented simple closed curve C that encloses the origin. So, let's start with an example. Well, what happens here? We have this curve, and we'll go around a circle of radius r. So, r cosine t, r sine t. Now, the rule was Green's theorem works as long as the derivatives of our field all exist and are continuous inside some slightly larger region. But what was our field? It was negative yi plus xj over x squared plus y squared. There is a big hole right here at the center. The function is undefined there, so its derivatives certainly don't exist, and that means Green's theorem does not work. In fact, if you calculate the curl of this, it's 0 everywhere it's defined. I trust you can do the quotient rule on this and work it out. If you did, P would be the I component, negative y over x squared plus y squared. And Q would be x over x squared plus y squared. And if you work this out, it will equal 0. So you want to say, it seems like the integral should automatically be 0 because the curl is 0. It's conservative. But it's not really conservative because it's got this one point in the center where it doesn't exist, and that's enough to break the entire theorem. So let's figure out what this integral would be. Well, if we did it the old-fashioned way, we'd say integral of f dot dr would be, all right, so f would be, let's see, how do we do this? Let's change this to polar form. F of r theta would be negative r sine theta plus r cos theta, ij, over r squared, which would be, in bracket form, negative sine theta over r and cosine theta over r. And the r, the parameterization we have up here. Notice the r vector is very different from the r scalar. R scalar is the radius at a point. Okay, so this would become 0 to 2 pi of negative sine theta. Let's pull out the r. 1 over r, negative sine theta, cosine theta, dot. Then we need dr. So r prime of t is negative r sine t, comma, r cosine t. It would be dot, I guess, r negative sine of or theta. We're using theta or t. I said t earlier, so I should probably be consistent. Or I seem to have mixed them up. Oh no, we'll use theta because we're in polar coordinates, so it doesn't actually matter what we call it. It'll come out the same. We have r sine theta, r cosine theta, d theta. Well, this r divides out that r. This r shouldn't be here. We factored it out. And so we get 0 to 2 pi of sine squared theta plus cosine squared theta d theta. Well, that's the integral from 0 to 2 pi of 1 d theta, which is just 2 pi. So the integral around this circle is 2 pi. And now what happens, we said, for any other curve, you can do kind of a funny little trick, which I won't go into great detail about why this works, but it basically means if you could stretch this circle out to some other form without crossing, without like pulling the across the place where it's undefined, you'll get the same answer. So like if we had a curve like this, you can kind of imagine what you would do is you would say, I want to do this curve here, and then at some point I would drop down to this, and I would go around in the reverse order, clockwise. And then I'm going to come back up and finish going around here counterclockwise. So you have kind of a compound path here, where first you go clockwise around this, and then you go counterclockwise around this. And the funny thing is then, your region is now this part. And it's continuous and well-defined on this part. All the derivatives are good. So you'd get a conservative vector field, which means the total answer would be 0. Which means this, going backwards, is negative 2 pi. So this going forwards must be positive 2 pi. Anyway, that's just a little topological trick that's not something you'll really have to do in this course, but I did want to emphasize the fact that if there's a place in your region where the field's undefined, then Green's theorem does not apply. You have to do it the old-fashioned way. Okay, let's do a few more examples here, and then we can call it. So, let's evaluate the closed curve integral y cubed dx plus x cubed plus 3xy squared dy following y equals x cubed from 0, 0 to 1, 1, and y equals x from 1, 1 to 0, 0. So, my region would look like this. I would first go, here's 0, 0, and here is 1, 1. Y equals x to the third, then back along this way as y equals x. So, you could do this with parameterizations, but we're going to do it using Green's theorem. So let's see. The curl of this would be del del x, del del y, y cubed, x cubed plus 3xy squared. So this becomes 3x squared plus 3y squared minus 3y squared. So 3x squared. So we're just going to have to do a double integral of 3x squared dA across this region D. So this one, you could do it as type 1 or type 2. It's set up to do y first, so that's how I'm going to do it. So I'm going to say 3x squared dy dx. Y goes vertically from x cubed up to x. And then x goes left to right from 0 to 1. Erase this part. The other method would be going left to right. You would say x would have to go from y to cube root of y. And then y would go from 0 to 1. Probably not too bad, but let's not mess around with cube roots if we don't have to. Right? 0 to 1, and then y equals x cubed to y equals x of 3x squared y dx. Because there's no y here, so the antiderivative would just be multiplied by y. Then we get 0 to 1 of, let's plug in x for y, so 3x cubed minus 3x fifth dx, which is 0, 1 of 3 fourths x fourth minus 3 over 6 x to the 6. So plug in 1, plug in 0, get 3 fourths minus 1 half is 1 over 4. That's our answer. Okay. All right. And now let's do one last one. To a semiannular region. So an annulus is like a ring. It's a circle with another circle cut out the middle. Semiannulus between the circles of radius 1 and 3, center of the origin in the upper half plane. Find the line integral of this complicated thing. Now again, when I see a complicated thing like that, it probably means that you're expected to do it using Green's theorem. This one's not as bad. You could do the antiderivative of arc10x. You could do the antiderivative of e to the y minus x squared, but it would still be messier. So let's do this with Green's theorem. So the region looks like this. We go from -1, 0 to 1, 0. And then we've got here 3, 0 to -3, 0. And these are two. It's an annulus here, but we only take the top half. So this is 1, 2, 3, 4 different parameterizations. So we're going to use Green's theorem to simplify it. And this is a thing that comes up a lot in complex analysis. You'll have all these complicated integrals, and you'll say, well, let's just do it with something like Green's theorem. And if there are any spots on the inside where it's undefined, those become how you solve it, because you know those undefined parts are where Green's theorem changes. Anyway, that's neither here nor there. We'll take the closed line integral of arc tan x plus y squared dx plus e to the y minus x squared dy. This whole thing is C. And if it's not said, always assume we're in the positive direction. It doesn't say positive here, but when it's just assumed. That's if it doesn't say. All right. So the curl here would be del x, del y, then arc tan x plus y squared, and e to the y minus x squared. So we go across, we'll get -2x minus 2y. This would become the double integral of -2x minus 2y dA across the region D. Now this is practically screaming that you should use polar coordinates, because the radius goes from 1 to 3, and the theta will go from 0 to pi. This is what we would call a polar rectangle. It is what a rectangle looks like in polar form. So we get -2 integral of r cosine theta plus r sine theta, 2 integrals. And then dA becomes r dr d theta, r from 1 to 3, theta from 0 to pi. I'm going to erase this top part now. So this then become -2. And we can factor out the r's, so we will get 1 to 3 of r squared dr. So I'm factoring an r out of here, so that's r squared. And then 0 to pi of cos theta plus sine theta d theta, which is -2. Then from 1 to 3 of r cubed over 3. Then from 0 to pi of sine theta minus cosine theta. Then become -2. 3 to the third is 27 over 3 is 9. minus 1 to the third over 3 is 1/3. And then if I plug in pi here, I get sine of pi is 0. Cosine of 0 is 1, so -1 minus sine of 0 is 0. Cosine of 0 is 1, so 1 minus 1. So -2 times -2 is 4 times 9 minus a third is 27 over 3 minus 1 over 3. 26 over 3 is... Hang on, let me make sure I've got my... Did I do the... Oh, this should have been +1 and +1. Let me check that again, because when pi, we get 0 minus cosine of pi is -1, so minus negative is plus. And plug in 0, we will get -1. Yeah, okay. There we go. So it's -104 over 3. And so when we're talking about the signs in these, whether positive or negative, I like to think of it in terms of charge. Like there's positive charge and negative charge, and it depends on which direction you go in as to what kind of charge you get. All right, that's that. We'll see you in class.